My topic is finite subgroup of F star as cyclic. So as I've already mentioned, we're looking only at finite fields here. We're restricting our domain to just finite fields. So before I proceed, I would like to recollect a few concepts of group theory. The first one is order of a group. So can someone tell what order of a group is? I hope my slide is reflecting now. I'm changing my slide.
Yes.
Okay, so what is order of a group?
The number of elements in its set.
Right. So if I take an example of say Z4, then the elements are 0, 1, 2, and 3. So there are 4 elements. So order of the group Z4 is basically 4. Then what is order of an element?
Least positive integer for which its exponent is gives the identity.
Right. So in Z4 again, if you consider the element 1, the order of the element 1 is 4. So that becomes the order of 1 is 4. Now the question is there a relationship between order of a group and order of an element in cyclic groups?
Yes.
Okay. What is it?
The order of a in cyclic groups, order of an element divides the order of a group.
Right. We can also say that in a cyclic group, there will exist at least one element whose order is equal to the order of the group. Right. Because in a cyclic group, we must have a generator, and that generator should be having that many elements as the group. So order of an element should be, say, for example, in Z4, as I've mentioned, order of 1 is 4. And we also know 1 generates Z4. Right. So in any cyclic group, if we take any element, if there will exist an element whose order will be equal to order of the group. Now, as our subject is field, so field is basically set under the operation of addition and multiplication. So what is F star then? F star is basically the set of all non-zero invertible elements of the field under the operation multiplication. But why multiplication? Can we define under addition? The answer is no, because in a field, once we are removing 0, that is the additive identity, we cannot define addition at all because the identity does not exist. So multiplication very well holds. So now the question is, does this form a group? Does F star form a group? Yes, it forms a group because it satisfies all the condition. First of all, it satisfies closure property because it is a well-defined operation multiplication. Moreover, associativity, identity, and inverse are derived from the definition of field itself. So it very well forms a group. Now what we're going to do next is Lagrange's theorem. So Lagrange's theorem, if we just brief on it, it just says that the order of a subgroup should divide order of a group. So we can say that the order of a group is a multiple of the order of the subgroup. But is the reverse true? That is, if I say for a group whose order is n, we take any divisor, say k, can we find a subgroup whose order is k?
No, not for not for any group.
Yeah. So we have a restriction, and that is for cyclic groups we can very well find. And that is given by the fundamental theorem of cyclic group. It also says that for every subgroup of a cyclic group is cyclic. Moreover, as I've already mentioned, if you take any divisor of the order of the group, we will have a cyclic group associated with it. Now, as I move on, I would like to introduce you to a notation, which is summation of psi of k over the divisors of n. So for now, consider psi of k to be just a function of k. So is my slide visible?
Yes.
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 Okay, thank you. So what does this notation say? Right. So for example, if n is the number, then the divisors of n are say k1, k2, and so on up to kn. Since we are considering only finite, we can say that n is finite number. So we'll have finite number of devices. So this notation simply says that it is psi of k1 plus psi of k2 and so on up to psi of kn. I hope it is clear. Yeah. So next we move on to the small proof. Okay, I'm not giving you a proof of this. I'm just giving you an intuition of the proof. So this is basically summation over the devices of n of phi of k is equal to n, where phi is the Euler's phi function and n is the order of a cyclic subgroup. So what is the Euler's phi function? What is that function?
It is the amount of natural numbers between 1 and itself, which are co-prime to
Right.
the given integer number.
Correct. So phi of k is basically all those numbers which are less than k and are relatively prime to k. So we're proving that if I take the summation over k, which is where k is the devices of n, you'll get n itself. So by fundamental theorem of cyclic group, we can say that for a divisor k of n, there exists exactly one cyclic subgroup, as I've already mentioned, and the generators, the number of generators is given by phi of k. Now, if I take n, the devices are say k1 as we did earlier, k1, k2, and so on up to kn, right? Now, by the fundamental theorem of cyclic group, we can say that we'll have a cyclic subgroup of this order, say C1, of C2, so on up to Cn. Now we look at those elements who generate C1. So basically, what are those numbers? Whose order is K1, right? All those elements whose order is K1 generate C1 in a cyclic group. So as we did Z3, so for example, Z3, both 1 and 2 generate Z3. So it is not necessary that only one element can generate a cyclic group. We can have many generators. So we're looking at all those elements which generates C1. Say we're calling it that set to be S1. Similarly for C2, say S2, and so on up to Sn. Okay. Now the question is, if I take any element from the group, am I right if I say that it belongs to at least one of these Si? I repeat the question. If I take any element of the group, am I right if I say that it belongs to at least one of these Si?
Yes.
Yeah. Moreover, if you notice, an element cannot belong to more than one also. So an element, because it does not have two distinct order, right? So an element, if you take, it belongs to exactly one of these Si. Also, can we say that from the same intuition, the intersection of any of these Si will be empty? Because an element
Yes, it
cannot
is
belong.
correct.
Right. So what we have done through this is we have created a partition of the set of the site of the group by S1, S2 up to Sn. So by the partition, we know that if to know the order of the group, say G, which is n as we've assumed here, is it correct if I say this is equal to cardinality of S1, of S2, and so on up to Sn? Yes. So what is the cardinality of S1 then? It is basically set of all elements which generates C1, right? And that is given by this phi of k. So this is nothing but phi of k1 plus phi of k2 and so on up to phi of kn, which is nothing but the summation over the divisors of n of phi of k. So with this, I've given you an intuition. It's not a formal proof, but you can easily write it down. So I'll just give you 10 seconds to just go through what we have done here. Now moving on to the theorem, the statement is finite subgroups of F star are cyclic, and here I'm considering finite fields. So for easy for my convenience, I've just named F star to be G and the order of F star to be N. So now if X belongs to G, then X is a finite order, say K. So the statement is true, right? It contains the cyclic subgroup created by X contains K elements because we know of this famous result. Now, I'm denoting this psi of k. Earlier, I just told to assume some function over k, right? So now I'm defining what psi of k it actually is in this proof. So psi of k denote the number of elements of the group whose order is k. Kindly note this definition is very important. Psi of k denotes the number of elements whose order is k. So can we say that psi of k will be greater than or equal to 0? To be specific, strictly greater than 0. Okay, greater than or equal to 0 to be general. Yeah, because every element will have an order, and for a field we can say this easily holds true. Also, we observe that the summation of psi of k over divisors of k gives you n itself, because every element will contribute to at most one psi of k, because as I've mentioned earlier, every element will have its own order. It will not have two distinct orders. So it belongs to at most one psi of k only. And we have defined earlier what phi of k is, which is the Euler's phi function. Now what we are claiming here is psi of k is equal to phi of k for any divisor k of n. Now if I take an element x of order k, then I'm taking r, which is relatively prime to k, then x power r is of order k. How is the statement true? That is, we know x is of order k and r is relatively prime to k. With these two statements combined, can we say that x power r is of order k? Yes. So suppose x power r order is say t. Okay. And we know x is of order k. So x power k will give me identity, and k is the least element. So if I take x power k of r, this is equal to e again. Now this is nothing but we can write it as x power r of k is equal to e. So from this we can say that k, we are taking x power r and we are operating it k times, we get identity. But we know x power r is t. We have assumed it to be t. So from this we can say that t divides k. Can we say t divides k? Okay, we can actually, it's a result in group theory. We can do that. Moreover, if I'm taking x power r, since this is x power r of t should be giving me identity again. So x power rt should be giving me identity. So again, because x order of x is k, so k must divide rt, but k and r are relatively prime. So from this we can say that k divides t. So from these two conditions, we can say that k is equal to t. Therefore, x power r is of order k. I hope this is clear to everyone. We can take a few seconds to understand. It's a very small proof. Okay. So from this, what we have done is, we have taken an element r which is counted in phi of k, right? Phi of k is basically set of all elements which are less than k and are relatively prime to k. So you've taken an element r which is counted in k, counted in phi of k, and we've showed that we can find x power r which is counted in psi of k, because we have defined psi of k to be set number of elements of order k. So from this we can say that phi of k is less than or equal to psi of k. Now, usually when we have to prove some a is equal to b, what we do usually is we say a is less than or equal to b and b is less than or equal to a, and by law of trichotomy, so it has to be equal. So with this you have proved one part. For the other part, assume fy, which is of order k, then y should be of some x power r form. Because otherwise, if you consider this equation, there will be k plus 1 solutions. That is x1, x2, and so on up to xk, and a y also. So it is a contradiction, right? Because it cannot have k plus 1 solutions. So y has to be of this form. So what we have done here is we've taken an element which is counted in psi of k and showed that it is counted in phi of k as well. So from this, we can say that psi of k is less than or equal to phi of k. Note that psi and phi are both counts of something. So we cannot, unlike subsets, we cannot say it belongs to. We have to say it is counted in. So what we've done here is it is y is counted in psi of k, and we showed that it is counted in phi of k as well. So psi of k is less than or equal to phi of k for any divisor k of n, because k is any arbitrary divisor. So these inequalities change into equality. We get this finally. Now as we move, so now we have established the equality. We are taking, instead of any divisor k of n, if we consider k to be equal to n itself, because we know n divides n, right? So we are taking for psi of n equal to phi of n. So since 1 is relatively prime to n, we say that phi of n is greater than or equal to 1. From this and this, we can say that psi of n is greater than or equal to 1. But recall the definition of psi of n. It basically says the number of elements whose order is n. So what we've shown here is we can find at least one element whose order is n. And what is n? The order of the group. So what we have found is we have established the existence of a generator of the finite field f star, proving f star is cyclic. Moreover, by the fundamental theorem of cyclic group, we can say that any subgroup of cyclic group is cyclic. So every subgroup of f star is cyclic. So once we know how important it is to know that if a group is cyclic or not, because many conditions, many properties can be studied if we know a group is cyclic. So this has made our process much more easier. For the finite, if the field is infinite, we cannot have a generalized theorem because some fields can be cyclic while some cannot be. So this is only for finite fields. So I hope the theorem and the proof is clear to all of you. The reference is taken from Kumresan sir's expository article. Anyone can refer that. And thank you.